Imagine the most elegant code you've ever written. Now picture it evolving, improving itself, generation after generation, tested against every possible edge case that nature can devise. Welcome to the Great Barrier Reef, Earth's largest evolutionary computing system, where 3 billion years of natural algorithms have created one of the most sophisticated living networks on our planet. As the sun rises over the coral sea, its first rays illuminate an underwater metropolis that would make any system architect marvel. Every coral formation you see represents not just a colony of living organisms, but the output of nature's most refined genetic algorithms. Watch as this morning light plays across a massive brain coral. Those intricate maze-like patterns aren't random, they're the result of millions of generations of optimization. Each ridge and valley precisely calculated to capture food with minimum energy cost. It's like watching the physical expression of an optimization algorithm, refined over countless iterations. But the real magic becomes visible as the day brightens. Fluorescent proteins in the coral tissue begin to glow, creating a living light manipulation system that would put our best optical computers to shame. These aren't just pretty colors, they're solutions to complex physics problems. Some proteins reflect harmful UV radiation, while others perform real-time wavelength conversion, turning harsh blue light into gentler red frequencies that penetrate deeper into coral tissue. It's the most elegant light management system ever evolved. As we move deeper into the reef, we encounter one of nature's most remarkable examples of distributed computing. A massive table coral extends its perfectly angled plates, each one solving complex calculus problems about light capture, water flow, and structural support, all without a single line of human-written code. The coral's solutions are breathtaking in their elegance. Where human engineers might need supercomputers to calculate optimal angles for solar panels, these corals have evolved living structures that automatically grow at precisely the right angles to maximize light capture while minimizing structural stress. It's optimization at its finest, written not in silicon, but in the genetic code of every coral polyp. But perhaps the most spectacular demonstration of nature's evolutionary computing power happens as the day progresses. Watch as the reef responds to changing light conditions. Each coral colony runs what computer scientists would recognize as a real-time genetic algorithm, continuously adjusting its relationship with symbiotic algae to maintain optimal energy production. When conditions become challenging, the system's true sophistication emerges. Some corals can actually swap out different strains of symbiotic algae like a computer switching between different processing units. It's live evolutionary optimization happening before our eyes, something our most advanced adaptive systems are still trying to achieve. As afternoon turns to evening, the reef reveals another layer of its computing prowess. Cleaner stations become active, where dozens of species demonstrate co-evolved behaviors that solve complex game theory problems. Small cleaner fish perform precise dances that larger fish recognize, creating a negotiation protocol more sophisticated than many of our computer networking standards. But wait until night falls, that's when we witness one of nature's most remarkable displays of evolutionary computing. Bioluminescent organisms create complex patterns of living light, each species having evolved its own precise signaling frequency and pattern to avoid interference. It's like watching a naturally evolved network protocol in action, solving the same kind of problems that challenge the developers of Wi-Fi and Bluetooth. And then, under the light of a full moon, something truly extraordinary happens. Across hundreds of kilometers of reef, billions of coral polyps prepare for their synchronized spawning event. This is evolutionary computing at its most magnificent, a vast distributed system coordinating itself with precision that would make any network engineer envious. Each coral polyp runs its own internal calculations, processing variables including water temperature, moon phase, tide conditions, and time of year. Without any central control system, without any direct communication, millions of individuals arrive at the same answer: now is the time. The resulting underwater snowstorm of coral gametes represents not just new life, but new iterations of nature's most successful algorithms. What makes this even more remarkable is how these corals pass on their improvements to the next generation. Through a process called epigenetic modification, corals can transfer learned adaptations to their offspring. Imagine a computer program that could pass its runtime optimizations directly into its base code. As dawn approaches and the spawning event concludes, we're left with a profound appreciation for nature's computational sophistication. Every coral branch, every symbiotic relationship, every synchronized spawning event represents solutions to complex computing problems that have been tested and refined over millions of years. The Reef reminds us that perhaps we've been thinking about evolutionary computing too narrowly. While we run genetic algorithms on our fastest computers, nature has been performing the same calculations in living tissue, achieving optimizations we're only beginning to understand. As the first rays of sun illuminate the Reef once again, we're not just seeing beautiful coral formations, we're witnessing the output of the most successful evolutionary computing system ever created. One that solves complex problems not with silicon and electricity, but with life itself. Next time on Digital Wilderness, we venture into Earth's most ancient deserts, where every grain of sand tells a story of natural computation, and survival itself depends on solving nature's most challenging algorithms.